to our respected lecturer and fellow viewers. We are from Group 5. Today, we are excited to present our MAT-099 group project, which focuses on the application of first-order differential equation. As we know, understanding population dynamics is crucial for urban planning and resource management. For our case study, we have chosen the beautiful city of Perth, Australia. Perth has shown the significant growth over the past 2 decades, and today we will use mathematical growth model to analyze its population trend from 2004 to 2024. In this presentation, we will show the secondary data we collected, determine the particular solution for Perth growth, predict future and past population values, and finally, analyze the factor influencing these changes. Without further ado, let's start our videos.
Moving on to data table. The data was collected over a period of 21 years, from 2004 to 2025. In 2004, the population was about 1.488 million people. Over time, this number gradually increased. For example, in 2010, the population reached 1.722 million, and by 2015, it grew to around 1.894 million. In recent years, the population continued to rise, reaching approximately 2.169 million in 2035. Overall, the trend shows a steady and consistent increase in population. This indicates that Perth has experienced continuous growth over the years, likely due to factors such as urban development, job opportunities, and migration. In conclusion, Perth population demonstrates a clear upward trend with no major declines throughout the period.
Now, we move on into part D, which is the calculation part. In step 2, we construct a mathematical model using a first-order differential equation, where we assume the rate of change of the population is proportional to the population itself. Therefore, our general solution is, which is P is equals to A exponential to the power of KT. When T equals to 0, which represents the year of 2004, the population is 1.488 millions. So by substituting the value into the equation, we obtain the value of A is equals to 1.488 millions. Next, we use another data point, which is the population in 2005, to determine the value of K. After substituting the values into the equation and solving it, we get the value of K, which is K is equal to 0.0153. Hence, the final models become P is equals to 1.488 millions exponential to the power of 0.0153t. Next, in step 3, we use this model to predict the future of the population. For example, to estimate the population in the year 2037, we substitute the value of T is equals to 23 into the equation. After performing the calculation, the predicted population is approximately 2,115,588. This shows that the population is expected to continue increasing over the time, following an exponential growth pattern. This prediction is useful because it helps us to understand the possible future trend of the population if the growth rate remains constant. Then, in step 4, we estimate the past population using the same model. To find the population in the year 2002, we substitute the value of T is equal to -2 into the equation. After calculation, the estimated population is approximately 1,443,157. This result shows that the population in the past is lowered compared to the present, which is consistent with the overall increasing trend observed in the data. This step is important because it allows us to verify whether the model can also represent past data, not only the future prediction. In conclusion, this model allows us to estimate both future and past population values using exponential growth, which is useful in understanding population trends.
Now, let's move on to the graph part. First, let's look at the dotted or straight line graph. This graph represents the actual population data of Perth collected over the years. From these points plotted, we can clearly observe a steady increase in population. This shows that the Perth population has been consistently growing over time based on real data. Next, let's look at the curve graph represents the model equation, which is this is the general equation, meaning it assumes the population grows at a rate proportional to its current size. As we can see, the curve increases more rapidly over time, showing accelerated growth. Now, Finally, when we compare both graphs, we can see that the model curve is very close to the actual data points. This indicates that the exponential model is a good fit for representing Perth's population growth. Both graphs show an increasing trend, but the curve helps us better understand and predict for the future growth patterns. That's all.
Based on our calculation from step 2 to step 4, the population of people in Perth are increasing over time. This trend is consistent with the actual value that we got from our research here. It shows that the actual populations of Perth are also increasing over time. Therefore, it can be concluded that the model values that we calculated and the actual values of the populations are both increasing over time. So, it shows that these both values are consistent. This statement can also be proven by the graph that we plotted here, that it shows that both of the values are increasing over time, that where both curves are exhibit similar patterns. Okay, next, based on our observation, there is a slight difference between the actual value and the value that we calculated. So, to find the accuracy, we will calculate the percentage error. So, we will take the value from year 2024. So, the actual data that we obtain for the population is 2,143,000, while the value that we calculated is here is 2,020,678. So the percentage area that we're going to calculate it, we will be using this formula here, which is the actual value minus the value that we calculated per the actual value and times with 100%. So the percentage, after we calculated, the percentage area that we obtained is 5.7%. So the error that we calculated is relatively small. So this model can be considered as acceptable for our population growth model. Do you guys want to know why there is a slight difference between the actual value and the expected value that we calculated? Okay, this is because in the actual real life, there is a slight change because of the migration reasons. Okay, I will explain because many other people from other regions or other country will likely to migrating to Perth due to Perth's stable economy. So when the economy is stable, there is more job opportunities and study opportunities for other people to immigrate to Perth, and causing the population of Perth become more increasing over time. In addition, growth in Perth has already been observed in the past. In the early 90s, many immigrants has already migrating to Perth because Perth already expand in the mining industry that already create more job opportunities to the people that migrate here. And in the future, Perth also expected to continue increasing in population because Perth is likely to maintain their stable economy, and also their stable economy in the mining sector, and also expanding their technology industry. So this development will create more job opportunities and also educational opportunities that can cause the population of Perth will be increased more in the future.
To conclude, this project shows how differential equation can be used to model real-life situations. By using the population data of Perth from 2004 to 2025, we were able to build a model to estimate past and future population values. From our analysis, the model follows the overall trends of population growth, although the predicted values are not exactly the same as the actual data due to factors such as migration, historical growth pattern, and future growth. Perth's strong economy, especially in mining and technology, continues to attract people, which may lead to further population increase. Overall, this assignment helped us understand how mathematical models can be used to solve real-world problems with the help of data and technology.